Hello, Maiken. Can you hear us?
I can hear you
Yeah,
very well.
it's my
Can
big,
you hear me?
yeah, we can hear you very well as well. So it's my big pleasure to introduce Professor Maiken Arendrup from Denmark. I think it is really not necessary to introduce her because it's the leading person in antifungal susceptibility testing in fungi. And we are really happy that you are here, at least online. We are a little bit sad that you cannot come, but we fully understand the reasons. And we are looking forward to your presentation. Thank you, Maiken.
Thank you very much. I can tell you that in Denmark we have an increasing number of patients that are infected with coronavirus. So actually I am speaking from home. We have been sent home, and that is the reason why I don't have video on, because my internet connection, I live in the farm side, so my internet connection is not good enough to both have video and speak reliably good for you. So I hope that you anyway can hear what I say. And what I'm going to do is, as Vit said, to talk about how we can test dermatophytes, the susceptibility of dermatophytes, and the advances that we have in this area. And if I could have the next slide, please. Then, as Vit said, you may ask, why at all do susceptibility testing for dermatophytes? Because most people think there isn't really an issue. So the first thing to try to convince you that there is an issue, and before you've heard all the other talks today that will substantiate this, I will just show a PubMed search for dermatophyte and resistance for the past more than 50 years. And you can see that there were almost none for the first 50 years time period here. But then during the last 10 years or 15, there's been a sharp increase in publications on dermatophytes and resistance. And the number I've indicated for 2020 is extrapolated from my search done by the end of August. So you can see there's definitely awareness out there now that there's something is going on. And if we move to the next slide, then I can tell you that also in Denmark this has been an issue. We collected the number of resistant cases that we were aware of in my laboratory, which is the reference laboratory in Copenhagen that serves the entire country. We are the only laboratory in Denmark that does susceptibility testing of dermatophytes. So we looked back in our records and identified 14 cases between 2013 and 18 and published those. And the majority of those are rubrum. And you can see the underlying alterations in the target gene to the right. And in agreement with others, we found most that contained or harbored alterations at the F397L or F397 locus in the target gene. And we also actually identified the one in orange in the bottom of the first table with a double mutation that hadn't been described before, but where the amino acids that are involved in this isolate are very close to where terbinafine dock into its target site in the protein, and that's illustrated on the protein modeling to the right. Now, these 14 cases were over a 5 to 6 year time period, and if I just go back to the 1st of January 2019 until today, then we have 23 more cases. So I think that documents very well that it's really important that we look for resistance and that there is increasing resistance worldwide, and that's most known in India, where a third of the isolates in some regions are resistant, and you're going to hear more about that in the next two talks. So my reason to have these slides were only to try to make you curious and about resistance and to understand that this is truly important, because whatever numbers we have, it's definitely an underestimate, because we know that so few laboratories actually do test dermatophytes. So if we move to the next slide, please, then you can ask, why don't we do susceptibility testing? Well, we you could actually say that susceptibility testing of fungi has been lacking years back, or after testing of bacteria, but for dermatophytes it's really terrible. And the main reasons is probably that it's a bit tricky. Dermatophytes are slow growing, so they often require 5 days in microdilution assays. Microdilutions assays are a bit difficult, and in part due to this slow growth of the dermatophytes, we also quite frequently experience contaminations with bacteria, with yeast, with other molds in our plates. An example of that is illustrated here, where we have the growth curve from a microtiter plate, where we have different concentrations on the x-axis of terbinafine and the optical density, so how opaque the medium becomes when the fungus grow, on the y-axis. And you can see that you have quite a nice line that goes from 8 to 0.5, and then you have spikes at 0.25, you have a spike at 0.06, and you have a high spike in the right of the diagram for one of the 4 positive controls where we have contamination. And it could complicate where you thought that something was really growing better if it was a first peak or the second peak, and also if you want to do an average of the growth control and you include a contaminated well like the one in the red with the arrow pointing at it, then the average becomes much higher than the actual growth by the dermatophyte. So contamination and slow growth, I think, are the 2 main reasons for susceptibility testing of dermatophytes having been so little uptaken by laboratories. In addition, of course, to not realizing there is a problem with resistance. So as we go to the next slide, then in EUCAST we discussed that probably that we might make it easier to do susceptibility testing if we used a selective medium. And as I'm sure you're well aware, then we in most plates used for dermatophytes, agar plates, supplement the plates with chloramphenicol and cyclohexamide to prevent both bacterial growth and most other fungi to grow on the plates. And in the following slides and the rest of the talk, I will refer to chloramphenicol and cyclohexamide as CC. And we use that to avoid contamination routinely in agar plates. So the EUCAST initiative on improving susceptibility testing of dermatophytes was to try to incorporate CC into the growth medium of the EUCAST susceptibility test format that we have for molds. And the most important thing when you want to evaluate some sort of new test is that that test is able to differentiate between susceptible, wild-type, normal organisms and those that harbor resistance. So initially we set up this test and we did a pilot study in my laboratory where we included some of the wild-type susceptible strains and some of the verified molecular mutants that we had of Trichophyton, rubrum, and interdigitale. And when we found in our laboratory that looked pretty nice, then we did a multi-center study to see that also worked in other laboratories. So we made a blinded collection, so nobody knew what was what, and then we circulated that to 10 laboratories in and outside Europe, and we got all their results back. And we wanted to evaluate as primary endpoints if we could correctly separate wild types and mutants across these laboratories, if there were any sort of potential interference with the growth in the microdilution plates when we added CC, and if CC addition affected the MIC endpoints compared to if CC was not added to the medium. And this whole principle is of course also based on the fact that CLSI, the American Organization for Susceptibility Testing, had formulated a susceptibility test method where they use round bottom plate and visual reading and this microtiter plate format. So we had an idea that this would probably be okay, but that it might be improved by a selective medium. So if we go to the next slide, please. Then you can see a list over the different isolates that we included. We have T. rubrum, the isolates of T. rubrum to the left and T. interdigitale to the right. all the different strain numbers, and in red are those that harbor alterations in the target gene that we know are related to a significant increase of the MIC, or sort of a strong resistance. The green ones are those that do not have any alterations, or in the case of interdigitale, the last three ones in interdigitale in the right side of the table, an alteration that doesn't affect terbinafine binding to the target gene. So those are wild type, they are susceptible. And in yellow or in orange, we have isolates that harbor an alteration for rubrum that elevates the MIC discretely, so it's sort of intermediate, you could say. And for interdigitale, we didn't actually have any sort of intermediate isolates, but what we realized later on was that two of our strains that actually harbor, or originally harbored, a significant mutation, the two in orange, that they actually were a mix of wild type and mutants when in the blinded strain collection. And when a patient develops resistance, unless he's infected with a resistant isolate from the beginning, then it's something that arises on the skin during treatment, and that can easily mean that you can have a mix of a wild type and a resistant isolate. And when you propagate such an isolate, you think it's just one. When you propagate that to prepare 10 tubes for circulation, then you pass it several times, and you increase the amount of growth. And if there is a growth advantage of a wild type isolate in a mix, then that will typically take over a bit during that propagation. That's probably what happened in these two. So they were causing some difficulties in the multi-center study, and you will see that. If we go to the next slide, then that summarizes the details of the method that we used. And it is, as I said, based on the method we have in EUCAST for susceptibility testing of moulds, aspergillus, and so on. So what is black here is basically the principle from the EUCAST E.Def 9.3 methodology, and what is in Turkish or bluish green color is what we did specifically here for the dermatophytes. So for those of you who do not know the methodology for moulds, then the principle is that we have a microtiter plate. We use two-fold dilutions of drugs, and we have a drug-free control. And the compounds that we included were terbinafine, itraconazole, voriconazole, and amorolfine, the topical agent. We use a medium that is an RPMI medium, and it contains 2% glucose, is buffered by MOPS. We do inoculum preparation exactly as we do for the moulds. And what I think is a little bit important to standardize the methodology across laboratories is that when we've prepared the inoculum, the Conidia suspension from a plate, we have a filtration step through an 11 nanometer filter that allows Conidia to pass, but not harmful clumps. So that means that it standardizes our inoculum very well. And I think that reduces interlab variation. For the multi-center study, we did such an inoculum preparation for each isolate, and for each isolate, we split it into two suspensions, each of 8 milliliters, so that we can inoculate a plate with and also without CC supplementation, so that we had a direct comparison with the same concentration of cells for each fungus in the inoculum. We chose to add CC, cyclohexamide, and chlorphenicol to the inoculum, so that when we inoculated the upper part of the plate, we had cyclohexamide and chlorphenicol in the medium, or in the tall suspension. I think in all laboratories who also do susceptibility testing of mold, this is a convenient way to do it, because it means that you can use the same plate you had prepared and frozen in your freezer with different drugs in it. You can use that both for molds, and you can use it for dermatophyte, because you make it selective by adding CC to the inoculum rather than to the plate. But of course, if you only test dermatophytes, you could just as well put it into the plate so that it was already there when you inoculate the plate. But then you would have to prepare both plates, batch of plates for dermatophytes and for molds. So that was the reason why we did the method illustrating how you can add it to the inoculum so that it goes into the plate after that. So we put that in the inoculum with CT in the upper part and the inoculum without CT in the bottom of the plate. We incubate it at 25 degrees. A single laboratory used 28, but the standard is 25 degrees, which is lower than we do for molds. And of course, with an extended incubation period of 5 to 7 days. And then for the multicenter study, we evaluated both a visual reading of the plate with a full inhibition endpoint, no growth at all in the plate, which is the standard for molds. But we also read the plate in ELISA reader and calculated a 50 and a 90% inhibition endpoint and read the MICs of that. So we ended up with 3 different endpoints. If you go to the next slide, then I'm sure that you will have the presentations after the talk, and here you can find the details on where you get chloramphenicol and cyclohexamide and the volumes that we used. So if we go to the next slide, please. Then on here, I've shown an overview of the MICs that were generated in the 10 laboratories of this strain collection during the multicenter study. And on the upper part panel, you have the MICs read by a visual complete inhibition endpoint. In the middle, you have the MICs you get if you use a spectrophotometer, 90% inhibition endpoint. And in the bottom, you have the endpoint, the MICs you get if you use a 50% endpoint. Then you have rubrum in the first panel, and you have the interdigitale, MICs for interdigitale in the right panel. And all the green bars are those that are for the wild type. All the black, gray, and gray bars are those that have strong mutations. And the yellow one for rubrum is the one that had the double mutation that we know only elevates the MIC a little bit. The first thing you can see if you, for instance, look at the green ones, the green bars, is that if you go for visual over spec 90 to spec 50% endpoints, you will see that the histogram, the bars, move a little bit to the left. Because if you allow more growth, as you do using a spectrophotometer 50% endpoint, then you need less drugs. So of course, your MICs go down when you use an endpoint that allow more growth. And that means, of course, that when we were finished with this, we would have to choose one endpoint, because if we want to set breakpoint, they will go with the method you use. The second thing you can see is that you have the green ones to the left with the lower MICs, you have the black ones to the right with higher MICs. That is what we want. And particularly for the spectrophotometer endpoint with the 50%, you have a very nice split between green ones to the left and the grey and black ones to the right. The yellow overlap both of them a little bit, in agreement with that we in general have a ±1 to 2 dilution variation in an MIC test, and this is an isolate with a sort of an intermediate susceptibility. So that's the reason why we see that. But overall, quite a nice split. For the interdigitale, you have some that are striped, green and black, and that is the 2 isolates that harbored both wild type and a mutant. And you can see they were quite randomly MIC classified, you could say, across the laboratories. Both some found it susceptible, some found it resistant. And I have to say that some of the laboratories who participated, they kept the strains for almost a year before they tested it. So it can also reflect that there has been a further change towards more susceptible, a high proportion of susceptible isolates in these mixes. But you get a nice split, and you definitely also get it with the spectrophotometer readings. And the good thing about spectrophotometer reading is that it's objective. So it will provide the same MIC independently on if it's you or if it's me, if it's an experienced or if it's an inexperienced reader. And I think that is a nice thing about an endpoint compared to a visual endpoint, where you will always have some sort of subjectivity in when you think something is completely inhibited. On the next slide, I showed the MICs for itraconazole. And itraconazole posts some specific issues, which you particularly can see for the visual reading, because here you have bars all over the concentration range. Normally, if we have a compound, then we want to see a Gaussian distribution that spans, let's say, 5, 6 MICs, but not 10, as you see here for the green ones. They go all the way. And of course, the color differentiation here doesn't really have anything to do with the itraconazole susceptibility, because it's still reflecting the terbinafine genotype. But the MICs for the visual reading goes all the way from 0.016 to 8 for both rubrum and interdigitale, and that suggests that there is an insufficient reproducibility of the MIC testing. And I think the reason for that is that when you look into these microtiter plates with itraconazole, you will see that there's none of the wells that have, for several of the isolates, that have a complete growth inhibition. So in many cases, you go from a tiny growth over many of the wells before you actually really see significant growth. But if you have a complete inhibition endpoint, then you would say, oh, but there is some growth here. So the MIC has to be even higher than that. And that I think is the reason why there is such a huge spread and device diversity in the MICs that were reported visually. And that is also because when the reason why the distribution is so wide for the 90% endpoint, because again here 90% endpoint inhibition only allows a little bit of growth in the wells. So because of this sort of background growth that there is in wells with itraconazole before it's completely arrested, gives this wide distribution. And that becomes better when you use the 50% endpoint. You see that they go to the left and you start to have a more narrow MIC distribution. So the benefit of the spec reading, that you have subjectivity, and the fact that you can more easily get a more narrow distribution for itraconazole, meant that for the method that we recommend, went for the 50% endpoint as the endpoint to be used for dermatophytes. So if we go to the next slide, then I'm going to show you some of the growth curves for various isolates. So we begin with a normal wild-type susceptible rubrum, and then we move to the different mutants, and finally to issues with contamination. And here you can see, what you can see here is that you have a flat curve. In the upper diagram, I haven't subtracted the background. So the background level is around 0.1 in optical density. And you start to see an increase of the growth curve when you move to 0.016, and then it goes up. The two dotted lines in the top are the mean of the positive controls, and the black ones in all these slides are the readings with terbinafine in a medium without CC, and the green ones are the MICs and the concentrations of the OD that we read when we have CC present. So you see the growth curve overlays each other quite nicely. And on the lower diagram, you see the percent growth compared to the growth control. And I've done a line for 50% growth, the gray one, the upper gray one, and the 10% growth, which corresponds to 90% inhibition in the lower one. So for susceptible isolate, you can see here that if you read it with a 50% endpoint, the MIC to the right would be less or equal than to 0.008. Whereas the 90% inhibition allows less growth, so it would be 0.016, and visual complete inhibition would be 0.03. But if you keep these figures in mind, then that is the level for a susceptible isolate. And on the next one, you see the intermediate-ish isolate, where the growth curve starts to rise a bit earlier. And also, again, you see quite nice agreement with the two lines here, a little bit better growth in the CC one, and that the MICs increase somewhat from what we saw before. And if you go to the next slide, you will see one of the more stronger mutants and examples of that, where you see that the growth curve starts to come up from the background level already at 1. So the MICs go up, and depends, of course, on which endpoint you use. But with 50% endpoint, the MIC would be 0.25 or 0.125. So it's within 1 dilution, with and without CC. That's what we typically see for microdilution assays. And another example on the next slide, where we have complete growth all the way. And finally, the last one I think I have here, with nice growth curves on the next slide, where you see it increases more rapidly in the beginning with a 50% endpoint. The MIC for this mutant is 4 or 2, dependently of you have CC or not CC included. So we go to the next slide. Then I have 3 slides that just illustrates contamination. And here you can see contamination in the black curve. You have a spike here that goes with a much higher optical density. If in this case, it wouldn't really complicate the endpoint reading because it doesn't affect the positive control, and it's not nowhere near where it crosses the inhibition lines. But if you go to the next one, next slide, then you can see that you start to see the growth curve go up and down over the endpoint lines, which complicates the endpoint reading. And if we take the last one, you'll see one that's completely awful, where you have spikes all over the place for the black one. And in none of these cases we saw contamination in the green one. This one has not grown very much, so it's quite early. But we of course stopped it here because we had so much growth in the non-CC wells for this particular isolate. So if we move to the next slide, then I think the conclusion on our multi-center evaluation was that we really saw an excellent correlation between the target gene genotype and the visual MIC that has used to be the standard for any sort of mold testing. But we also saw a very nice correlation between spectrophotometer MIC and the visual MIC, which is promising for a spectrophotometer endpoint. We also saw no significant alteration in the growth curves after the addition of CC, and we saw no contamination in the wells where we had CC. And I have to say that is with the caveat that we used a strain collection that had been, subcultured before we used it. So I can't say that it's as successful if you use more primary isolates, more or less directly from the patient plate. But based on this, we have established a formal EUCAST method that is now called E.Def 11.0 and has just been published 2 days ago. So it's really timely compared to this conference. And we've also established QC ranges for control strains, which is really important so that you can, if you set this up, that you can see and that your method is working. And we have also set tentative ECOFs, and both of these will be available soon at the EUCAST.org website, free for everyone. And on the next slide, I've just shown what these looks like and which isolates have been included. And you can see. And we've also established QC ranges for control strains, which is really. I'm sorry, but now I have my. Now I think they've turned it on. I'm sorry, but I had my previous talk into my ear. But you can see here that we have control strains both for, and ranges both for flavors, so that you can check your plates with a 2-day incubation, but also that we have for interdigitale and rubrum. And these strains will be available freely, or for a small charge, I think, at the strain collection that you can reach at CCUG. And also we have set tentative ECOFs, so that you can use these ECOFs to say if your organism is normal or if it's non-normal. ECOF is the upper limit of a wild-type susceptible organism. And that is, so even though we don't have breakpoints yet, you can use this as a guide of when you do susceptibility testing, if your isolate is wild-type or not. And that was my last slide, so I just want to, if you go take one more, to say thank you to you for your attention, and also just to notify all the people who has been behind this work.
Thank you very much, Maiken. Yeah, everything is very exciting, and we have many questions here on Slido, but unfortunately we have time maybe for few questions. So, what is the cycloheximide concentration used? What's your opinion on using mycelium maceration for testing non- and low sporulating dermatophytes?
Yes, the concentration you can for cyclohexamide and chloramphenicol is the same as typically used in plates, and it is in the presentation. So I think you can just download it there and get the specific concentrations. We have for molds, we know that if you that there can be differences in MICs if you use a conidia or if you use a mycelium. So this is the first step for microconidia-forming dermatophytes, and that's the reason why we use filtration.
Yeah,
We also know that it can be difficult sometimes for rubrum to have enough microconidia, and therefore we typically, if we have a difficult isolate, we inoculate several plates in order to be able to harvest enough spores for running the susceptibility test.
yeah.
So future work will have to focus on what to do for Microsporum, for instance, and how to standardize that properly.
Yeah, thank you. And the last question, when do you expect the real breakpoints will be available for terbinafine and azoles?
That's a good question. And breakpoint setting in EUCAST depend on MIC distributions from at least 5 laboratories. So as soon as you guys start doing MICs and share your MIC distributions with us in EUCAST, we will be able to set breakpoints. But we need MIC distributions from several labs and at least 5 before we can set breakpoints, because we have to ensure that it reflects what you do out in real life.
Yeah, thank you very much, Maiken. Maybe after workshop we will send you the remaining question, and if you will have time, we will post your responses somewhere. We will in touch. It's up to you.
By email or what?
Maybe by email or in some discussion on the website. We will let you know. Thank you very much.
Okay, that's good. Thank you very much.
We hope that you enjoy the rest of the workshop.
I'm sure I will. Thank you very much.